Good morning, everyone. Let's get started. I see lots of computers. That's good because we're going to be working with WMS again today and then also on Thursday. As a reminder, that first WMS assignment is due on Thursday, and then I'll give you a second WMS assignment to be working on over the Thanksgiving break, which is next week. Is that a surprise to anybody that we don't have school next week? It's the only thing that allows you to keep going, right? One foot in front of the other. All right, so today what we're going to do with WMS is we're going to move beyond just loading images and downloading elevation data. Hopefully by now you feel pretty confident in your ability to pick a spot on the map. Maybe that's where a culvert's going to go in, so like a crossing location. Downloading the elevation data and delineating the watershed that feeds into a certain point. And remember that sometimes it's an iterative process. If you don't zoom out far enough, then it could be that you're truncating the actual watershed, and so you have to go through the process again. So what I'm going to do in the activity that I'm going to hand out to you, I tell you the coordinates of the culvert. And so what you're going to have to do is find that location on the map and delineate the watershed that feeds it, and then once you get to that point, once you've delineated the watershed, then we're going to go through and set up a rational method model on it. So we're going to estimate the peak discharge, just assuming a typical C value for the watershed. We'll put in some rainfall data, and we'll find out what the peak flow is. Are. All right, so if you don't feel so confident in delineating watersheds, I'm going to be going through that same process on the screen, so you can feel free to watch as I do it, or if you have questions, just raise your hand and I'll step over and help you out. If you'd given me some advance notice, I could have maybe brought one in today, but I didn't. Okay. So if you drop your outlet like on the main stream or too close to it, then it'll delineate like the entire contributing area. So you got to be maybe 1 or 2 blocks away from the main stream that's running along Blue Sulphur, because what we want to do is we want to get the stream that's running along Liken's branch before it gets to Blue Sulphur. So see, this stream we know is on the west side of Blue Sulphur, so we're sizing the culvert that's passing the water from the Liken's branch watershed under the Blue Sulphur road. So, pixel placement in this case can have a pretty big effect. So what we're looking for is your watershed should be on the order of about 265 acres. And that'll vary slightly depending on what DEM resolution you chose. I chose the 7.5 meter DEM. I think the default, based on how far you're zoomed out, probably it suggested 15 meter resolution to you. I'm always a little bit like, well, I'll just take a little more time and go for slightly better resolution. So I'm just curious, for those of you who chose the 15 meter resolution, what did it choose? What did it say the area is? 263, 262? All right. So in the magnitude of things, we're talking far less than a 1% difference, and so it's probably fine. And we've got enough relief, there's enough topography in this area that we're probably okay with the coarser resolution. Where it really matters is where you have relatively flat terrain. That's where it's really important to have the finest resolution, but it being so hilly here that probably we'd be all right with the 30 meter resolution. All right, so we have our watershed delineated, and remember how we could trim the DEM, because I've got a lot more elevation data there than I actually need. And I'm going to turn off the street map now too. So I'm just going to disable the street map, and I'm going to trim that DEM by right-clicking up here under terrain data, the active elevation model, and trim with a polygon that I interactively just draw around the border, double-clicking at the end, and then it trims away that. And so I can zoom to the extents. Let's see. And remembering to frequently save, because it could crash. Yeah, I don't know. There used to be a button that would view. I don't know where the zoom extents button is. Just got to do it manually, I guess, for now. All right, so we've got this watershed, and here's what we know about it. I've got the instructions on the handout I've given you. We're going to go into the Hydrologic Modeling module. We haven't done much in there yet. It's this button across the top that the reason it looks the way it is when you actually prepare the schematic of watersheds. This is different watersheds feeding into various outlets. And so across the top, click on the Hydrologic Modeling module. Okay. Mm-hmm. Mm-hmm. Yeah. Yeah, go back into the wizard. Okay. And here under choose outlet locations, there's delete outlet point. And I think if you move that out of the way, you can click that. Yeah. Okay. Yep. Mm-hmm. All right. So we're in the Hydrologic Modeling module now. And over here on the left side, the context-specific menus have changed. And what we want to do is use the Select Basin tool. Right now, by default, it's on Select Outlet. But click on Select Basin. And you can't see it because the text is right on top of it. But there's a symbol there. They put it at the center of the basin by default. What we're looking at is kind of like a schematic of a watershed. And so if I turn off everything else, it's saying here is a basin that goes to an outlet. That's this model, is some basin that's connected to an outlet. And so if you double click on that basin, right now by default it assumes we're going to do a HEC1 model. So we need to change that using the drop-down box to rational as the model. And now still under select basin, we'll double click on the symbol for the basin in question. And you'll notice that it's already filled in some of the data here. Remember, the rational method is Q equals CIA. So WMS is acting as a preprocessor. It's going out into the world and it's finding all the data you need to satisfy the questions, what goes into Q equals CIA. So the area here is automatically filled in. The runoff coefficient, let's just assume that we've been out into the field and we've observed the watershed. We're familiar with the type of vegetation that's there and the soil that's there, and so we decided that we're going to use 0.6 for the runoff coefficient. Now, runoff coefficients are inherently kind of squishy, and it's not really reproducible and defensible in the same way that curve numbers will be when we automatically calculate curve numbers using land use and soil type data. So there isn't, in other words, there isn't a way to automatically calculate a C value. So we just have to be aware of that. It's just by double clicking here on the basin using select basin tool. Oh, see, originally it was like this. The basin was behind it. And so when you're on the select basin tool, you single click on it and you can move it aside. Or you could turn off the text. The other way is by turning off the text. If we go here into the display options, you can go into drainage data and just uncheck all of these labels so they're not in the way any longer. Okay, well. The street map?
Yeah. Well, not the street map, like the...
Oh, you're talking about the elevation? Yeah, it's here under terrain data. You can click it on and off.
Okay.
Yep. Okay, so what we need to do is bring up the rational method details. Has everybody got this open? Yeah. Okay, so remember what we said is we're going to have a runoff coefficient of 0.6, so key that in. Now the time of concentration, it can calculate that based on basin data. So here, compute T sub C based on basin data. And it brings up some different ways of estimating the time of concentration. And so what we're going to use is, let's switch it here. Instead of saying time of concentration, there's a formula for lag time. And lag time and time of concentration are related to each other by the fraction 3/5. And so if we know one, we can calculate the other. But the SCS method, if you switch it to compute lag time and then go down to the SCS method, it has automatically filled in all of the things that we need to use the SCS method to calculate lag time, except it doesn't yet know the curve number. So when we start getting land use and soil type data into WMS, it would automatically calculate that as well. But let's just manually enter that in. So you'll notice it's calculated already the watershed length. It already has the watershed slope. But the curve number, we're going to have to enter here in the variable value box. So in the handout it says, let's assume a typical curve number would be 75 for this area. And so as soon as you enter 75 and then browse to another location, then it calculates the lag time for this watershed based on the formula that's shown. It summarizes here in the window what's the lag time formula for the SCS method, and it's using this lot length, this curve number, and this slope. And you could override those values if you happen to know that there maybe is some problem with your data and you want to adjust it. But in our case, the watershed lag time is going to be 0.26 hours. Okay, and then when you click OK, it copies that 0.26 hours. It converts it to minutes. Did it though? 0.26. Oh, okay, yeah, that was lag time. So it converts it to time of concentration, right. So that's why here the T sub C is 25 minutes, is because time of concentration is 5/3 the lag time. So it converted that lag time in hours to time of concentration in minutes. Okay, so now we need the rainfall data. So compute IDF curve. So if you click on that, then it's going to go and get the data that we need for this location. It's set to Hydro-35. If you click Get Online Data, it should go to the precipitation data frequency server for us and go and pull the rainfall data for our watershed. So it's like it knows the location in the world, and it goes and gets that IDF curve and imports it directly. So if you think about it, that's pretty slick compared to like Bentley, when we had to kind of manually type that in after we got the data from the website. So that's kind of nice that it does that. If it doesn't, you can always define the storm data yourself in the same way that we did with, like in the homework assignment, where you use the 2-year and the 100-year, and it kind of interpolates in between. So it could do that interpolation if you went and manually got the IDF data for the location. But so it's got that for us. And so what we need to do is compute the intensity. So you select like the 10-year curve in our case. So you just select the row for the 10-year, compute intensity. So based on the time of concentration that we previously calculated of 25 minutes, it's extrapolating between the 15 and the 30-minute. And so if we look, we can see it's going to be somewhere between 4.28 and 2.97. And so it already extrapolated based on the time of concentration. So it's going to be an intensity of 3.22 inches per hour. And you say done, and it copies that intensity here. And so now we have the peak flow rate. See how in the window it's saying the flow rate would be 515 CFS? And yours will probably be slightly different if you had a different area, but probably not too much different. Now the final thing is we can have it compute a hydrograph. And if you click on that, just move the window to the side before you click on compute hydrograph. So click compute hydrograph, and just use traditional method for routing. That means if you're combining multiple watersheds together, how long should the travel time and the delay through the stream be? In this case, we just have a single watershed, and so we don't really need to account for a separate delay as the water travels from one outlet to the next. So just use traditional and click OK. So after we click compute, it brings up this hydrograph that if you double click on that, we need to close this. Double click on the hydrograph, then it shows you traditional triangular shape that's associated with the rational method. So it just goes up to the peak, and then it immediately declines back down to 0 flow rate. And that's the rational method. It typically overestimates. If we're going to do a more sophisticated analysis of this watershed, actually using land use and soil type, it would probably be less than this. But they talk about sometimes all you need is just a rough estimate. And we've essentially delineated the watershed, and we have calculated the time of concentration. We've obtained rainfall data, and we estimated the peak flow, and it only took, well, about 20 minutes, 25 minutes. And so now if all you need is a rough estimate, and they're looking at a culvert, and it's a 3-foot diameter culvert, and they're just wondering, oh, what's the peak flow rate going to be, then you'd be able to really quickly say around 500 CFS, ballpark. So that's the value of the rational method. So let's save this so that you've got it as an example of a functional rational method model. So you click Save, and wherever you indicated as the location for saving, it's created now a couple of different files. Oh man, Windows File Explorer is just wrecked on this machine. Same as the other classroom I work on. Anytime I want to browse files, it's not doing so great. So, all right, so that's the rational method. What we could do is we can add an additional outlet and break the watershed up into parts. And so if you turn the page, I show you that there's a couple of other spots where what we're going to do is subdivide this watershed into smaller pieces. And so I'm going to, by the way, I'm going to delete that hydrograph that's there right now. So there's this button on the left, select hydrograph. And when you've got the hydrograph selected, if you just push the delete button, then it doesn't delete it. No, wait. I thought it did. Okay, well, it used to. Let's subdivide the watershed. I'm going to turn the map back on. And what I want to do is break it up into different pieces. And so where I'm going to put those new outlets, now you can go through the wizard, or you can go into the drainage module, and you can create outlets with the tools that appear over here on the left side in the drainage module. So you could go back into the hydrologic modeling wizard and choose outlet locations and create outlet points. But a lot of these same tools that are available through the workflow guidance of the wizard is available in other places too. So here under the drainage module, what I'm going to do is I'm going to create outlet points here and there, and then I'm going to delineate the watershed again. So I'm going to go into the hydrologic modeling module, and once I've dropped those two additional outlets, click on delineate watershed, and it warns you that it's going to delete everything that was there before as far as the data of the area of the watersheds and so on. All right, so what it's done now is it's calculated subbasins. Even if it's not turned on, the DEM data is still available to the computer. So remember, I wasn't displaying those contour lines, but it was still there in the background so that the computer could go and get the data. So, you know, maybe there are some reasons to subdivide the watershed. You know, the rational method works best when you have relatively small basin sizes. It's not really applicable for a watershed that's 300 acres. But its performance is better for relatively smaller watersheds. And so if we have 3 subdivided watersheds and then we model them separately, like maybe we know that this lowest basin is the most urbanized. So if you turn onto the second page of the handout, I've given you different C values and curve numbers. So if this has more houses and we assume it's going to be more impervious area, then we can get an accurate idea of the watershed as a whole by using different C values and different times of concentration for each of them. So what you can do is go back into the hydrologic modeling module, and once you double click on one of the basins, it will allow you to, well, we can do all of them rather than just the selected. So here under show, you can do either selected or all. We can expand this. And so the lower basin, maybe it helps at this point to rename them. So 4B, that's the one that I'm referring to as the upper left. And basin 5B is my upper right. And then 6B is the lower basin. So in the handout, what we have is different runoff coefficients for each of them. So the upper right, for example, I'm going to use a runoff coefficient of 0.55. the upper left, 0.40. And then the lower basin was the one that's maybe more highly urbanized, so I use a higher C value, 0.70. Mm-hmm.
Mine is like popping up with, I don't even know, like 4 different labeling systems, and then the 7C, like it's not popped up in my rational method menu. But I don't see 7C.
Are you looking at the outlets under type or basins? All right. Yeah. If you double click on an outlet, then it'll bring up this model in terms of the outlets rather than in terms of the basins. So when you have the 3 basins shown, you can change the runoff coefficients, and let's calculate the time of concentration using the basin data. So you'll click compute, and you'll have to scroll down to lag time, SCS method, and then put in the curve number for each of them. Now, right now, I'm working on the upper right basin. All right. So the upper right basin was the one that had 75 for the curve number. And that allows me to calculate now the time of concentration is defined. Yeah, there it is, time of concentration. All right. Now, upper left. Lag time, SCS. Upper left, 0.70. Lower basin. So when you subdivide the basins, it becomes a little bit tedious. Now you have to do everything 3 times. You have to calculate the time of concentration 3 times. You have to do the IDF curves 3 times. So compute intensity.
What type of method do we use?
For the time of concentration,
Yeah.
you go to lag time, SCS method, and then you're going to have to enter in the curve number. So this one, which one did I just do? Upper right. So upper right, lag time, SCS. Upper right was 75. Why are the intensities different for all of these 3 different basins? The C value doesn't affect the rainfall intensity. That's right. It's because we have different times of concentration. And the worst case scenario is a storm duration that lasts exactly the same length as the time of concentration. So that's what it's picking up on, is we've calculated the time of concentration for each of these watersheds, and then it's finding the intensity that's going to correspond to the maximum flow that comes out of each of the watersheds. So now, if I've done things right, then what I should see is out of the upper left, flow rate of about 140 CFS, and that's what I've got. 143 is what it's coming up with. And it'll vary a little bit depending on where you drop that outlet, because that's going to affect the area. The lower basin, about 210 CFS. The upper right basin, about 220. So, you're not what? change this from outlets, change it to basins. All right. Now, I think you may have more. Okay. Did you have an extra outlet someplace?
I think like right.
Yeah. So it's so close to a border that what it's done is it's split the. You have to kind of go a little bit away from where streams junction. So it's close enough to a border that it's picked up a fourth watershed. And that's okay. It's relatively small. It's only 0.39 acres, so you can kind of just ignore that one. So if you go back, if you open up that dialog again, so you use this and double click on one of the basins, and then leave it that, but then all, yeah. So you have to keep track of which one is the small one and just ignore that.
Okay.
Okay. Can you zoom in? Yeah, just right on there. Okay, and let's turn this on and see what we got. That should work. And those are both outlets, right?
Mm-hmm.
Let's calculate Topaz again.
Okay.
See if maybe that helps. Now, all right, so what it's saying is that you've got some outlets there. Oh, that one. You can't have an outlet just in like a random spot. So zoom back out again. That.
Oh, I see.
So you need to delete that, and then you'll be able to do it. So for each of these activities that we have today, you have the list of instructions of like what to click on and in what order, and I'd encourage you to practice this. You know, like find some watershed that you're interested in and practice making a rational method model for that watershed, just so you can cement in your mind what is the workflow that you need to do it. All right, so the next one we're going to do is National Streamflow Statistics, and there's a DEM file that I've put onto MU Online that you need to go and download. So go to MU Online and log into our class page. Rather than getting it from the online data that's available, I just wanted to demonstrate to you that, you know, if you want to give someone an elevation model file, you can do that. So here under WMS items, we're going to DEM file for hurricane. So click on that. Guess we maybe need to right-click on that because we don't want to display it. But that is kind of interesting. So right-click, save target as, and find a location that you're going to be able to browse to. And it saves it as a file extension GDM. So I guess what you can see is that this DEM file is just a text file really at its heart, where each location is where the elevation is known in a grid. So I've downloaded this hurricane DEM file.gdm, and we're going to save WMS, save what we were doing, and then create a new project and open up that DEM file. So browse to the location that has hurricane. Where did I put it? C temp. All right, there it is. Hurricane DEM file. And then it just loads that elevation model already clipped It's the watershed that we're going to look at is enclosed inside of it. Okay, so basically what I had done is downloaded it through the online data, and then I trimmed it, and then I exported. Once you have a DEM model, you can right-click on it, and there is Save Digital Elevation File. So, different pieces of your model will be automatically stored when you save a WMS project file, but if you want to like spin out just a piece of it rather than the entire project altogether, you can kind of like export the digital elevation file. So that's what I did. So what do we do at this point? If we want to delineate a watershed, we have the elevation model. What's the next step? That's right, Topaz. So Topaz is what is going to be analyzing every pixel and figuring out which adjacent pixel is lower, because that's the direction that the water is going to flow. So it kind of just for each cell is identifying a flow direction. So we go here into the wizard and we do compute flow directions and accumulations, so Topaz, and you compute Topaz. And this may take a while because it's a pretty big DEM file. Oh, this one's faster processor than my office computer, I think. And then what it'll do is it'll show all these flow accumulations where there's at least, in this case, 5 acres upstream. Okay, so close this and zoom in on the left side of the watershed, because you can look at like what direction is the water flowing. The water is flowing to the west. And so here's the main stem of this watershed. And this is just some smaller watershed here. And let's change the flow accumulation just to get a feel for what are the mainstream and what's just like the side streams here. So let's change it to 100 acres and apply to display. Now you can see, all right, this is the main stem. Let's change it to 200 acres. Apply to display. And doing that will help you pick the right spot to put the outlet on, because before, like if we had it 3 acres, it's less obvious where we're going to be putting the outlet. I could accidentally click here thinking, well, that's to the left, but that's not the real outlet. Like the stream that we want to delineate is the one that has a lot of upstream area. So all those minor ones kind of don't show up anymore when you change the accumulation threshold to a higher amount. Okay, so the next thing is we're going to create an outlet point just here, almost to the limit, but not all the way. And once you've dropped the outlet point, delineate watershed. And it'll go through the process of following the ridge lines. And it's calculating. You can see it's kind of going slowly here to calculate the maximum flow distance. What it's doing is, remember when I dropped the little blue stream thing and it shows you the flow path? I showed that in a previous class period where you can click somewhere on the map and it'll show you what direction the water is actually flowing. Right now, what it's calculating is it's doing that for every cell in the network. And it's calculating how far is it if a raindrop falls here to the outlet. How far is it if a raindrop falls here to the outlet? And it's just going through that one cell at a time for the millions of different elevation points that we have in this watershed. So that's why it kind of takes a while. Probably I have more resolution, more elevation resolution than I really need, considering how big this watershed is. If I'm not mistaken, this is the spacing was the 7.5 meter resolution, and what we've got is like 50,000 acres. So this is a really large watershed. So it's far too big to model with the rational method. But if you want a quick and dirty, kind of just a real rough idea of what the runoff is going to be, we can use national streamflow statistics. And so we have the watershed delineated, and what we can do now is go here into the drainage module. So it's, remember these buttons across the top, the drainage module, and okay, let's go into the hydrologic modeling module first and switch the drop-down box to NSS. This is where before we had chosen rational method. This time we'll do NSS. And in West Virginia, there are 3 different regions that the USGS has, they've done like a statistical analysis of streams using stream gauge data and rain gauge data. They've kind of looked at about 100 different watersheds in the state and extrapolated the relationship between watershed area and peak flow rate. The region that this watershed is in is a region that's called the Western Plateaus. So double-click on the basin to bring up the dialog box associated with national streamflow statistics. It's that double-click before that we used to bring up the rational method window. This time, though, because the drop-down box is on NSS instead of rational method, when we double-click on the basin label, it brings up a slightly different window. So I'm going to pause for a moment and make sure that everybody's on the national streamflow statistics. So change it from Alabama, so scroll down to West Virginia, and then there's a publication that USGS has put out. It's like 110 pages long for the state of West Virginia, where they show all the calculations they went through to determine what area and what peak flow rate you can expect to see. So it already knows the basin area. So here, see how it says 80 miles, 80 square miles? That is the area that it got from us delineating the watershed in question. So it's put that area down here into this formula, and scroll down to, we want to have the peak flow Western Plateau.
Why would my area only be
7 square miles? It might be that your watershed outlet is in the wrong spot. Could be that your projection is off. Yeah, it's because, see how you're in feet right now? The watershed model was in, yeah, it's the projection issue. So you need to go into the, for some reason it didn't remember that you're in zone 17. All right. Yeah, so I guess it's kind of worth checking. It usually remembers what zone you're in and what projection and so on. But if you're in feet and the DEM you're bringing in is meters, then the areas it calculates will be wrong. So what we're looking for is this peak flow Western Plateau, and we know the area. And so click on Compute Results. Let's see. So select that and Compute Results. And now what it's done is it's calculated for instance, a 5-year storm. What's the peak flow? About 5,000 CFS. For the 10-year storm, the peak flow will be about 6,200 CFS. So of the list, you have to click over here to make it a selected location, and then you compute the results. And all it's doing is it's just a regression equation that is based on the area. So this is only valid for watersheds that are mostly rural. If you have an urbanized watershed, or if you have like a dam or any kind of like reservoir flood control structures in here, like if you have a lot of places where people have ponds on creeks and so on, then this won't give you accurate results. It talks more about what these NSS equations are if you get the publication for the state in question. But so this is just another way to really quickly come up with an estimate of what the peak flow might be for a certain return period. You can see this goes all the way up to a 500-year storm if you scroll down through the list. So 500-year storm, we'd maybe see around 14,000 CFS. So you probably wouldn't make a culvert to pass that flow. But.
What does equivalent years mean?
Yeah, I don't know. That's an interesting question. I'm not sure what they mean by equivalent years. I'll have to look into that and get back to you because I'm not absolutely certain. Yeah. I don't know. I guess we could always click help and see what comes up. Equivalent. Yeah, I don't know. Yeah, it might be related to the range of the standard deviation. That could be it, you know, like where the error is 30%, and so it could be that the size of that error is 8 years or something. I don't really know. It doesn't seem to hold, though. If you look at 36% standard error for the 500-year storm, I really don't know. I'll figure that out, and I'll report back on Thursday. Okay, so let's say that we want to export this results into Excel. So you see that that's one of the options here, export. That's one of the things that WMS is pretty good at, is preparing the data so that you could analyze it in another way. So let's just find a folder that I'm going to be able to find this again. So it's called NFF export, National Flood Frequency Export. I'll save that and then try and open that up in Excel just to see what it gives me. So it's that same table that we were looking at where it has the return period. It's got the peak flow rate, the percent error, and then this mystery column, the equivalent years. But it's basically just a report of your analysis where we've got the drainage area. It's got the 80 square miles that we know, the state that we picked, which peak flow region we're in, and so on. So there's 3 different geographic regions that the state is broken down into. And the other options, if we scroll down a bit here, there's the Central Mountains. So the Central Mountains would be like Beckley, Cranberry Wilderness, that sort of area. And then the Eastern Panhandle is just totally different geography because it's really flat out there. So they have a different National Streamflow Statistics equation for the Eastern Panhandle. And then these other ones like East, North, South, and so on, that's just old methods that have been replaced. The most recent publication, I think, was the 2010 publication. And so that's the best one we've got for really just empirically predicting what the runoff is. All right, so save this one so that you have National Streamflow Statistics. So we'll say NSS example. Maybe should have saved that earlier because you never know when it's going to crash. And let's do TR-55. Now with TR-55, we're getting into the territory of that's actually the model that they run over at the Division of Highways for some of their smaller watersheds. You know, they wouldn't necessarily just use the rational method because you can do TR-55 quickly enough that there's no sense in using an inferior method when the preprocessor can set everything up so easily. So create a new project and make sure you're in zone 17, units of meters, and use the wizard to delineate the watershed that's shown on the image I've given you. So the best way to figure out if you're in the right spot is look at the highways. The highways can give you an idea of like the geography and how far you need to zoom out. Now, I'll be doing it on the screen so you can watch me. but I'm not going to talk through it. I'd like you to delineate that water, to find the outlet and delineate the watershed, and then we'll come together and go through the TR-55 of part of it together. It's easy to accidentally get too big of an area. That's what I did. My Topaz finally just finished. It took 25 seconds, which is an eternity in Topaz years. So this is the watershed that we want to delineate. What's the name of this road? Garrison Avenue. Anybody know where that is? I don't. Yes, correct. So we're going to delineate this watershed just before it goes under the interstate. That is our point of interest. Hard to believe that just a week ago, it was just program crashing, nothing was working. Finally, we're doing stuff. It's beautiful. All right. So about 980 acres is what we ought to have. And of course, you can trim that DEM if you want to throw out the stuff that you don't need. I'm going to trim my DEM here. Oops. Go into the Hydrologic Modeling module, And this time, instead of, we're not going to do rational, we're not going to do NSS, we'll do TR-55. And so now it knows it's doing TR-55 so that when you use the Select Basin button and double-click on that symbol that's hiding back there behind the text, double-click to bring up, it has the TR-55 modeling dialog box. And so just like before, there are certain things that it can go and calculate based on the data that you have in the background. So for example, right now it doesn't have the time of concentration. So let's fill that in the same way that we did when we were using the other methods. So you can click Compute under Basin Data, and let's use the SCS lag time method. So change computation type to lag time, scroll down from Denver to SCS. And let's assume that the curve number in this watershed, instead of 90, it's an odd default, 68. And the other stuff it already knew based on just the elevation model. So 68, so it comes up with a time of concentration of 1.1 hours approximately. The drainage area it already knows. Now what we have to do though is put in some rainfall data. So let's change it to rainfall distribution. See where it says type 1. Temporal distribution, we live in a spot that has type 2. So we need to change it to type 2 because that's the Midwest. And then the rainfall depth that we want to figure out is from the precipitation data frequency server. I'm surprised that there isn't a way to automatically obtain that. So we'll actually have to go to the precipitation data frequency server. It surprises me that that's not automatic. All right, West Virginia. What we want to do is find the 25-year rainfall depth nearest to the time of concentration that we already have. So we have about a 1-hour time of concentration. So let's go with the cursor on Charleston, go down here to the table. The 25-year storm is this column. We want the 1-hour depth. So this is a depth of 2.13 inches for a 1-hour storm, 25-year return period. So 2.13 inches is what we'll put in here for the rainfall. You know what? No. That's not supposed to be the, we need to use the 24-hour storm depth. Now that I'm thinking about it a bit more, I'm pretty sure it's supposed to be the 24-hour storm depth because it's using the type 2 distribution, which is a 24-hour period. 4.16 for the 24-hour storm? All right. So put in 4.16. For the rainfall, 4.16. We've got 1 minute. All we have to do is click Compute Hydrograph. And now, it's not that stupid triangular hydrograph that we had for the rational method, but this is a hydrograph that maybe is a little more realistic because it's the 24-hour distribution. Now, why don't we have any like no runoff for so long? It's because the 24-hour storm, remember, assumes that there's very little rainfall at first, but then there's this sudden period where most of the rain is coming. So this is a 24-hour runoff for a 24-hour rainfall. So we'll revisit TR-55. We kind of had to rush through it just now. We're out of time, but we'll pick back up when we get together on Thursday with another TR-55 example. And then we'll move into actually how do you calculate the curve number using WMS, which is where it really begins to shine. That's all for today. I'll see you on Thursday.